All right, another short video here. This time we want to talk about frequency charts and levels of measurement. So I have some notes here. We'll go over frequency charts. I'm going to share my screen with you, and hopefully you can see that. So here we're talking about some variable. The variable here is the score obtained on some sort of exam or aptitude test. And the possible scores here are 0, 1, 2, 3, 4, and 5. So the variable is the score on the aptitude test. The individuals in this sample are the 80. If you add up these numbers, you're going to find 80 individuals who took this test. The variable is the score on the test. So to create a frequency table, which leads to a frequency chart or a relative frequency chart, we just count the number of individuals that scored 0, and we put that number here. The number of individuals that scored a 1, scored a 2, a 3, a 4, and a 5. Okay, obviously, if we add all these up, we're going to get the total number of individuals, in this case, 80. Now, the only difference between frequency and relative frequency, the relative frequency is basically the percentage of individuals that fall into a certain group. So the 24 people out of 80 gives us a relative frequency of 0.3 or 30%. 16 individuals got a score of 1. 16 out of 80 is 20% or 0.2. And similarly, we see the other relative frequencies here calculated. If we add those up, depending on, and if we rounded too much, we're going to get something very, very close to 100% or 1.0. Now, from this table, we can either create a frequency chart. If we label the categories here, if we called this, again, these are the scores, right? 0 through 5. Here I have a relative frequency chart. I am graphing these numbers, 0.3, 0.2, 0.25, 0.15, 0.0625, and 0.0375 on this scale. So the people who scored 0 are 30%. The height of this bar goes up to approximately 30%, 20% for bar here for 1, 25%, and you can see the relative sizes of the bars. Now, if I put frequency on this vertical axis, the shape, the relative sizes would be the same, right? Because 24 is going to give us 30%. Again, 16 is less than 24. The highest frequency is 24. The next highest frequency is 20. So if you did a frequency chart here, you get the same shape. The only difference would be the numbers on this vertical scale. All right, this is just a second example of the same thing. In this case, there's only 40 individuals. We count up the frequency of observations. In this case, the scores go from 3 to 10. And here are the frequencies. Once again, the relative frequencies are the percentage of observations. So in this case, 4 out of 40 gives us the 10%. 6 out of 40 gives us the 15%, and so forth. These numbers will add up to 40. These numbers will add up to 1.0 or 100%, depending on how we want to look at it. Again, this is a relative frequency chart, charting these numbers on this axis. If you put the frequency on this vertical axis, you will get the same shape graph with the bars showing the same relative heights. All right, so that is frequency charts. So let's go back now to our board here and look at levels of measurement. Levels of measurement is something we want to know about. The 4 levels of measurement are nominal, ordinal, interval, and ratio. So you might be given a particular set of data and asked, what level of measurement does this rise to? So you're always going to look, you're always going to kind of start here and say, is it nominal? Does it have order? So you start here and you say, does the data you're looking at have any order to it? Can it be ordered in any way? If it can be ordered in any way, it reaches the level of ordinal. Okay? So nominal data has no particular order to the data. An example of that is if I ask the class, what is your major in college, right? You're going to tell me computer science, you're going to tell me engineering, you're going to tell me art, you're going to tell me, you know, air conditioning, whatever it is. So there's no real order you can put to that. Obviously, we all know mathematics would be at the top of the list, but that's a different conversation. Eye color, again, blue, brown, green, whatever it is, you can't really order it, right? So nominal data has no particular order to it. If you can order it, but you can't do math on it, then we call it ordinal. So stuff like where surveys, you're answering a question, is the service here excellent, very good, fair, or no good? It has an order, right? Excellent is the top, very good is next, fair is next, no good is last. So we can say it has order, but math makes no sense. We can't, there's no, you can't say what's the difference between these two, anything like that. And basically we focus on differences when we say can do math on it. Right, so there's no math that can be done on these particular examples. They would be called ordinal. Now, if you say, okay, it has order, and I can kind of make sense of differences between the data values, then it reaches the level of interval. Interval data has order, and differences make sense, but ratios do not. So this is a little bit tricky because we're talking about the difference between things that are on a linear scale that kind of rise at a constant value. It's like when you have your car on cruise control at 30 miles an hour, you're going a constant 30 miles an hour, as opposed to something that's not linear, that isn't going at a constant speed, that you're changing, you're slowing down, you're going faster and such. So things that are on a linear scale, you can make sense of differences. All right? Like a temperature, I'm sorry, a linear scale reaches the level of ratio. If it's not a linear scale, but you can talk about differences, then it's an interval scale. So it has order and differences make sense, ratios do not. So think of temperatures. So we can say 80 degrees is 60 degrees more than 20 degrees. That makes sense, right? More, 60 degrees more. But we can't say that it's 4 times 20 because it's not a linear scale. Temperature does not rise at a constant level. And that's something, if you're not familiar with logarithmic scales or exponential scales, it's a little beyond this class, you don't need to know it. But realize if the scale is not linear, it's not a straight line, you can say it has order and differences make sense, but it doesn't quite reach this top level of ratio. Ratio means that you can take differences among data and ratio. So something like test scores, heights go on a linear scale. Differences make sense. You can say you are 6 inches taller than me. And if you're 6 foot tall and some kid is 3 foot tall, you say, yeah, I'm twice as tall as this person, or this 3 foot person is half as tall as the 6 foot person. So those are the levels of measurement that you want to know. All right, keeping it short. See you next time.